going to say now is very important. This is part of the class I started about 3-4 months ago about stochastic processes and application to molecular and cellular biology. So today we are at the problem of escape from an attractor. So I want to go to a particular question and I will motivate it from neuroscience, where it comes from. So I think this is lecture number, I don't know, X is equal between 5 and 8, I forgot. So something between 8 and 9 and 11, let's say. So just to remind you what we discussed previously, we looked at the stochastic process. You have a stochastic equation, x dot equals b of x plus sigma of x w dot, which is the Brownian noise. This is the drift, deterministic drift. And let's say this is the tensor, diffusion tensor. And so what we have looked in the previous classes is the problem of escape, which is a classical escape problem since Kramer or even Arrhenius, but really Kramer 1940 discussed this question. You have the case where all trajectories of the deterministic dynamical system are attracted, let's say, to a point P, which means B here of P equals 0, let's call it P0. And P0 is an attractor. And here we have the normal outside. And on the limit cycle, we have, it's not the limit cycle, but on the boundary of the domain here, that we call omega, we have n dot b at each point P. This was negative. So all trajectories are coming and converging to that point. And now the questions that we have solved last week, I mean, it took us really 2 or 3 lectures, is to calculate what is the mean first passage time, starting from x, so the expectation of the time, where tau of x is the first time. That if you look at the trajectory, and so we looked at the question when sigma of x could be written like 2 square root epsilon, where epsilon is a small parameter and no dependence on the position x. So tau of x is the first time that the first time t positive, that x of t is located on the boundary condition that, let's say, it started at position x at time 0. And now if you look, if you're interested in the mean first passage time, so we said that in the limit of small epsilon, asymptotically, there was a constant k epsilon, and we found the value of the psi here divided by epsilon, and psi was related to the minimum. So we looked at this when b was the gradient or minus the gradient of a potential, let's call it phi. So this is what we did last time. When b is the gradient of the potential, then psi was something like the minimum of phi on the boundary minus the minimum of phi inside. And the minimum of phi was here at the point P0, and then you have to look at the minimum, if there's any minimum. I mean, there is, but if there are several, it can be achieved at different points on the surface here of the boundary, on the boundary. Right, so this is what we found. We discussed this last time. So this is very, very well known. And now I want to look at the case where we have an attractor. And the question is, why do we want to do this? Now I would like to motivate this question by a problem in neuroscience that we looked at a couple of years ago. And in particular, what happened when the attractor is not inside the domain, but it's located close enough to the boundary. And why is it important? We will see, because then the entire classical WKB approach to calculate this problem fails. doesn't work well. And now how do you study this? So in 2 hours that we have, I will not be able to do all the calculations. I'll present some calculation I will detail, and some I will present the general outline. All right, so now so this is to review what we did before. Now let's discuss about the motivation, which comes really from neuroscience, which is a distribution of what is called up and down state. So for this, so what are up and down state in neuronal network? So if you have an ensemble of neurons, so you have neurons that are connected, they form a network. So the big question, of course, that nobody knows, I mean, there are many questions in neuroscience that are unknown, but basically, what are an ensemble of neurons doing? It's unclear. It depends, of course, on the region of the brain where you are. But if you record, for example, continuously, you will see some activity, what is called spontaneous activity. And in particular, so this is like a neural network, very schematic. And if you record, this is now a time series recording. This is the voltage of a neuron. So you stick an electrode, and just I'm going to show you what you see from here. You can see what is called up and down state. That is, instead of having the membrane potential at minus 60 millivolts, you see some type of activity where the potential is spending some time at minus 40 millivolts, and then goes back to minus 60. And then there's this transient. And of course, what is the meaning of those transients? Why you can have something at the order of, let's say, 1 second to 2 seconds that have this depolarization. That depends on the network. If you can show that if, for example, you cut the connections, you don't have any more this type of activity. I mean, there are also intrinsic properties, but basically what we're saying here that this is a network property. Now, for understanding this, the first thing you would like to do is to have a model for having this kind of behavior. A model based on the analysis of the neuronal network. So about 10 years ago, a bit more, we proposed a model for a neuronal network that could produce this behavior of up and down state. So when you are at this state, this is called a down state, you are down, and this is called an up state. And so the models is based on the property that when two neurons connect, they connect, as we have heard in Jim's talk, Jim Rotman's talk 2 days ago, they connect by synapses. And at synapses, you have the release of a neurotransmitter from vesicles. And when the vesicle is released, and of course, if you have many action potential, that a succession of action potential, which happen when, for example, a neuron is firing, so a succession of action potential that should contribute to free the neurotransmitter. At some point, the number of vesicles that is there cannot follow anymore this ensemble of action potential. And this phenomenon is called depression. So depression is a physiological property by which the number of vesicles that you would like to release cannot anymore follow the rate of action potential. All right, so now the idea of the model of depression, so that you have a variable mu between 0 and 1, that will give you this, that will measure, that will account for this possibility to release vesicle. So this is the, you can think about it as the probability to release vesicle. All right, and so to build the model, you need to have another variable, which is either the voltage or the firing rate of the neuron. And here the idea is that you use a mean field model that is, instead, you can do a model for each neurons, but you can write also, if the ensemble is sufficiently connected, a parameter which is the voltage and is mu for the ensemble. And so I'll give straight away the equations that the differential model is. So you have for the voltage, there is a time constant to recover from equilibrium, which means that you recover like exponentially. This is what this term is. Plus a constant J, which accounts for the connectivity. Mu is a depression variable that I will write in a second. R of V is the conversion from voltage to firing rate, plus a noise term, which is sigma W dot. And so I will explain in a second all the terms here. Mu, this is the how this variable evolved. So if nothing happened, it should converge to 1 exponentially with a certain time scale TR. And mu is a parameter. U is a constant. And R of V again is the conversion of voltage to firing rate. And here, I think I'm missing a mu. Yeah. So those are parameters, they are constants. J is, this is called the connectivity, the mean number of connectivity. This is a neuronal connectivity. And this is really just phenomenological model. Like Hodgkin-Huxley is a phenomenological model. So this is basically, this measures the noise. What is this noise exactly? How it is related to the physiology? This is not clear, but basically it accounts for all the noise that occurs, the noise of synaptic noise, the voltage noise that is embedded in here. Right? And RV, the conversion, is just like V minus the threshold, the positive part of this, which means V plus is this. This is V plus. Right, this is this when V is negative, this is 0, and otherwise it is V when V is positive. So, when you have a large firing rate, the voltage evolves, so mu starts to, so here, if you wait for the system to evolve, when mu is going to, when you have a large firing rate, this is going to lead to a minus, so this will decay. So you start to be, the number of vesicles available is going to be depleted. And so it's going to be very hard for your system to feedback and to fire. So now I'll give you, again, this is the motivation for the mathematics we're doing today. You can ask, what is the phase space for this? What is the phase space? And what is the, how can this generate this behavior? So for this, again, I'm not going to show the detailed analysis of the phase space. So the phase space analysis is just by putting the noise to 0. And you can start to look at the critical point by putting V dot equals mu dot equals 0. And you just have to solve this equation. So the phase portrait, phase space. So let's call this equation 1. Turned out to be quite surprising. And again, for the phase portrait, this value of these parameters that I'm not giving here that are confined in table, when we found them, they were calculated from looking at physiological experiments. So they were coming with precise values. So this is 0, this is mu. So the phase space is mu and v. So this is going from 0 to 1. And so what we found is that there was a place that they are basically, depending on the value of j, you can have, there's a Hopf bifurcation for the critical parameter. So I'm showing you the phase space after you have the Hopf bifurcation, where you have basically a limit cycle. Here you have an attractor. So I'll discuss in a minute where it is located. You have here a saddle point, and it goes like this. And here you have another attractor, which is the resting state. And this is an unstable limit cycle, and it's depending, of course, on the parameters. So this comes, if you think about where this separatrix came from, it came from something that was, cycling around this limit cycle, and this is what you get. So this is the phase space. Again, one attractor, one saddle point, and another attractor. So let's call it A1, let's call it A2, and this is a saddle S. All right, so what happened?
Where is T? So this thing's going to...
What is T? Yeah, I'm sorry, the T here?
Yeah.
Yeah, T, let's fix it T to 0.
Okay.
This was just a threshold that comes from, but let's ignore it for a second. I mean, I'm not going to, it affects the picture, but I'm not going to discuss much here, the T here. Okay, so now, from this, what you can imagine, if you have now a noise, you had the noise in the system, then of course you can look at trajectories. The trajectories that start here in the neighborhood of the attractor can escape, and they have to, then they can, once they are past this separatrix, they do a big loop and can come back to the attractor. Or when they do this big loop, they can enter into this region, which is the a limit cycle. So here you have a basin of attraction. And then when you fall into here, when you pass exactly the limit cycle, you fall into this attractor. So this region here corresponds exactly to this up state. Each time you are up, so obviously you're going to have some oscillation, which is predicted by this damped oscillation here. And now this is the why we've been motivated by this question, and this is the class of today, is how long are you going to stay in this region? How long, and how can you calculate this? Once you leave this region, it turns out that this separatrix is very close to the, so again, I didn't invent this. We looked at it with the simulation. It's very close here to the limit cycle. So most likely when you reach this region and you can pass it, after some time you will also pass this, and then you will go back to this attractor without making any other loop. And those big loops are called, in neuroscience, this is like a population spike, that you go around this big region. All right, so now the question is, what can we say about the time of those events? The time the system is up. And what can we say about the distribution of this time? So this is the motivation. What can be said about the distribution of time in the up state? So again, we now have a model for this to start answering this question. So now, 10 years ago, we did some simulations, and I will show you now the result of the simulations. And then this is the motivation for redoing this analysis. When we looked, so this is the result of simulations. Of numerical simulation, you have your system, you just run many simulations, you look at the time in this up state, and what we found something like this. So this is the histogram, this is the time in the up state. Now the question was why? This is not what was predicted by the classical theory of escape from a limit cycle. So it took us about 10 years to go over all of this and to start understanding what is the meaning. Why you have picked? Okay, first of all, let's go back to the classical escape problem. What do we expect? So the classical escape, which is this question, if we look at the distribution of exit time, the distribution of exit time, let's call it P of t, is actually exponentially distributed, and tau here is exactly the mean first passage time what we calculated here. So this predicts that the escape time should be a single exponential. Now where that was coming from, for this we had to plot the phase space correctly. And it turned out from the parameter, and this is, so now I'll give you the right positioning of the phase space for the attractor, for the upstate. Metric, the distance do matter, not only the topology of the point where you can say that you have a focal point, but why the distance do matter, because it turned out that when we looked at it correctly, the cycle, the focus, which we called here A2, the focus was positioned very close to the attractor. Right? So then we understood what happened, and this is now the goal of this class, is to show mathematically that what we're going to describe now is mathematically consistent and correct, and how we can then from this calculate these peaks, where are they coming from in terms of the eigenvalues of the associated Fokker-Planck operator associated to the dynamical system. So this was the phase portrait. This was the unperturbed dynamical system. Everything was looping toward that point. And of course, when we had this trajectory perturbed by noise, you can imagine what happened. If this distance here was of the same order as epsilon, which is the size of the noise, since in this region there is no field, B is 0, we are in a region where the field is sufficiently strong, so the noise is small, but here the noise start to be significant, and then there's a certain probability that the trajectory escape. While if the trajectory do not escape, then it has to go around, and then of course we will be interested in calculating what is the distribution of exit points. So what can happen? The trajectory goes around with almost a probability 1 and come back to this region where it can escape again. So then we can start to ask the mathematical question, is it true that basically the rotation here, which is associated to the imaginary part of the Jacobian when we linearize the field at that point, is this connected to the peak, the distance between the peak here that we have? And is it true that the distribution of exit point is concentrated in a small part here of the boundary and nothing around? So those are the questions. So this is the motivation of the analysis I would like to present today. So let me write the questions. And so why is this actually relevant in neuroscience? I mean, not that we understand where this is coming from. The idea is that pretty soon we are going to have continuous recordings of neurons in the brain. So, you know, there is no new technology to have a microscope embedded in the head of an animal, and you can record for hours. Now, how do you analyze continuous recording? What can you say about the local networks? So the idea is that, this is an example, if we have up and down state, if we plot this up and down state in here, if I have time I will show how to do, otherwise this is published. From the distance between the peak here, we can come back to some information about the mean number of connectivity. That is the mean number of connectivity. If you have an ensemble sufficiently connected that have this property, then the idea is that we could use the distribution of this event of up and down state, and from the mathematical analysis, if this model apply, because in general there are more than just the depression, there are more properties of synapses, but there are systems that are well characterized by depression only. Then the idea is that from this peak here, which I haven't shown you how to do, but you can basically extract the J. And why is that? Because actually what I said is correct. The rotation here, if you look at the matrix here, at the point where it is 0, if you linearize it, it's going to have it's going to be of order 1. It has eigenvalue and eigenfunction. The eigenvalues are going to have a real part and an imaginary part, which you can imagine that the imaginary part will depend here on this variable. And if the other are known, basically the idea is to recover from the distance between the peaks some information about connectivity. All right, so this is the motivation for today's mathematical analysis about this kind of question. So let me write the question that we will be interested in. So first question, what is the distribution? What is the distribution of the exit point? That is when the trajectory exits, where is the distribution located? Is it located uniformly? The answer is, we will see no. As the point here is closer and closer to the boundary, the distribution is going to get picked at a point which is the minimum distance between the attractor here and the boundary. So what is the distribution of exit point? First question. Second question, we can ask what is the mean exit time? What is the mean first passage time? And the third question, which is not contained in this, would be if we have peaks here, what really we need to calculate is really the profile of the distribution of exit time. And this is contained in the entire, in the spectrum actually. So the first question, the third question is, can we compute the probability, the distribution of exit time? I call TE the exit time, probability that this is equal to T. And this requires to calculate the eigen values of the operator. So the first question, how to calculate, how to compute the spectrum of the Fokker-Planck operator. So why this is a non-trivial question? Because if you have a limit cycle, so maybe I should write the Fokker-Planck equation for this equation. So the Fokker-Planck equation is the probability distribution function of the couple V and mu. So the Fokker-Planck equation is a solution of dp dt equals, so in general, if we have a dynamical system which is x dot equals b of x plus square root 2 epsilon w dot, this is epsilon Laplacian p minus the divergence of b multiplied by p. And so there is, and we have the boundary condition is p equals 0 if you're on the domain omega. So this is the equation on the domain, and we have here the absorbing boundary condition on the omega. And the distribution of exit time is usually the integral over omega, and if you differentiate this divided by time, this is exactly this probability that the time equals t. So this is what we have. Basically, if you ddt, this is the divergence of the flux, so this gives you exactly the flux here. So why this is not trivial? Because in this case, B, when you have a limit cycle, cannot be a gradient. And if it cannot be a gradient, what do you find? So if you have a gradient, basically you can always transform the question of finding the eigenvalues as a minimization problem. You minimize the quantity for the first, the second. But if you don't have a variational formulation, we have to, you cannot use all of this technology. So again, it took us a couple of years to understand where and how to find the eigenvalues of a non-self-adjoint operator. This operator, when we'll have this, because of the limit cycle, cannot be put into a variational form because B will never be a gradient of any function. And so the problem, if you look in the literature about the problem of finding the spectrum, it's mostly open. The spectrum of a non-self-adjoint operator. So how to compute the spectrum of the Fokker-Planck operator, which is really non-self-adjoint? All right, so this is the motivation. And now what we need is to analyze the equation. Basically, let me remind you the important equations for each of the questions we have asked. So the distribution of exit point, you remember we looked at this in the class, it was maybe class number 2 or 3. We have an equation for the distribution of exit point. That is, if we solve this equation, we answer this question. And so let's now write what are the partial differential equations that are needed to answer the different questions here. So for the question number 1, the distribution of exit point, what is the operator? I think we had them on the first class, right? Or second class. This was, so if we wrote this as an operator, let's say L of P, this is the L of P is this operator as a function of P. So L of P, or L star of P, what was in the note? This is L star means the adjoint with respect to the L2 integral. So this was equal to 0 on omega. And we had to have like a condition like P of x on the boundary equals delta of x minus y. And this, the interpretation of this was P was the probability that the density probability that a particle escape exactly at point y. Right, so this is classical calculation. So if we know how to solve this, then we could have an information about the distribution of exit point. For the mean first passage time, I want to show that we have a family of equations, and the solution is going to be basically what is called WKB form. And then we can use WKB to look at the different asymptotic solutions. So for the mean first passage time, the equation is L star. So L star, so let me write it L star once. This is epsilon Laplacian P plus B. So this is self-adjoint, and then you have to integrate by parts to get this term, which is B gradient P equal minus 1. And P, let's call it U. And U equal 0 on the boundary of the domain. So if we know how to solve this, U of x will give us the first passage time condition that the particle started at position x. So U of x is exactly the mean first passage time condition that the particle started at position x. All right. Now, so we have mean first passage time, distribution of exit point. To get this distribution of exit time, then we need basically to solve the entire Fokker-Planck equation, the time-dependent Fokker-Planck. And formally, what is this? What is the solution formally? The solution we can always expand in this in the basis, assuming that we know a base for this solution. So let's suppose that at time 0 we have P x t condition of y. P, I suppose that you start at position y at time 0, which means this is a delta Dirac at x minus y. So P formally what we get is that p x t conditional y. So we know that the first, so if we have a positive non-self-adjoint operator, we know that the first eigenvalue is going to be real and of dimension 1. So we can write it this way, exponential minus lambda 0 t. And then we have u0 of x, v0 of y, plus sum of n and m, exponential lambda n m. And so this is t, and this is u n m of x, v n m of y. So the u n m are the eigenfunction of L, and the other one, v and m, they are the eigenfunction of L star. Okay, in principle here, the eigenvalue are not real, but so this is real because the first one, as I told you, is real, and this is of dimension 1. So what we have in here is, I'll take the real part of this. And here, of course, no, this is what you get. Yeah, V can be something of this type, which is the conjugate value for V. So in principle, it's not enough to, so what is lambda 0? Lambda 0, this is the first eigenvalue. And the first eigenvalue, so those are the classical properties. Lambda 0, so lambda and m are the eigenvalues. And it turns out that lambda 0 is real. So if this is real, this means that if we integrate this with respect to x, and we can differentiate to get this probability of exit time, this will give us something that can only decay. So we should not expect any information about the oscillation coming from this, because this is decaying. However, those terms here, that's are not real, they have an imaginary part. This is what we are interested in calculating. So we are not interested in calculating the first eigenvalue, which is actually 1 over the mean first passage time. So it can be shown that this is 1 over tau, the mean. We're interested in calculating the other one. So how to calculate, how to compute the lambda and m. All right, so let's continue 5 more minutes and then we'll break, and then we'll continue after the break. So how to calculate the lambda and m, which are obviously solution of the eigenvalue, eigenfunction, which is here for u, it's L, u and m, equals minus lambda and m, u and m. This is the this is the eigenvalue problem. Okay, so at the beginning we saw that this was a difficult question, so we wanted to have a model for this, a general model that we've used. So let me give you this model, and then I will write this down to have a generic dynamical system where the critical point can be arbitrarily close to the boundary. How do you build it? How do you find it? And then I want to spend time using WKB. So WKB is a certain form to a certain form for the solution, U and P. And I would like to use this to show you how you can calculate where the equation for the eigenvalues are coming from. It turned out that it came as a surprise. This equation is hidden in what is called the boundary layer. This is an equation that actually lives in the neighborhood of the limit cycle that we have missed, us and many people, for many years, because it was hidden in here. And by resolving this in what happened in this boundary layer, you can find explicitly an explicit expression of this eigenvalue as a function of the property of the vector field along the limit cycle. So before doing this, let me show you, let me present to you the generic model.